fun theories.
Okay. So let me start by thanking the organizers for the invitation and the opportunity to speak. It's always a great pleasure to be in Paris, one of my favorite cities. So in this talk, I will summarize some work that appeared in this preprint some time ago, and that was done in collaboration with Jerkovic, Ishtiaki, Karasik, Komagorski, and Pufu. So in this talk, we will tackle a long-standing problem in supersymmetric quantum field theory, which is the computation of, or the solution of the chiral ring of, in particular, four-dimensional n equals 2 superconformal field theories. Okay. So in this talk, I will summarize how you can find an exact solution for a simplest class, or the simplest class of non-holomorphic local observables that you can define in these theories. I will essentially present is an algorithm how you compute these observables exactly as a function of the coupling constants of the superconformal field theory. And by coupling constants, I mean the constant, the coupling constants that preserve superconformal invariance, which take values or define what we will use, what we will denote as the conformal manifold of the superconformal field theory. So here will be an example, for example, for a theory with one modulus. And in this space, typically is acted on by dualities. So it's quotiented by some S-duality symmetries. And as far as I know, this kind of exact solution of correlation functions that we will present is the only example I know of non-perturbative solutions of field theory correlators above 2 dimensions at finite n. So let's start with some background and setup for this work. So the basic object that we will be considering is a special class of operators that exists in supersymmetric theories, which are called what are called the chiral operators. So these are operators that are essentially annihilated, but half of the Poincare supercharges that any supersymmetric field theory has. Okay. Of course, a lot of work was done in the 90s and 2000s studying, unraveling the properties of supersymmetric field theories. But one can broadly summarize the progress that was made during that time as progress in the determination of the moduli space of vacua, which is the space of supersymmetric ground states of these theories, and in the exact computation of holomorphic observables, essentially the one-point function of precisely these chiral operators. So the vacuum expectation value of a chiral operator in some non-trivial vacuum state. Just to remind you, two of the milestones in this era were the exact proposal of the solution for the low energy effective action of Weishaberg and Witten of four-dimensional unequal gauge theories, and the ab initio derivation of this solution by Nekrasov and Okunkov are kind of two of the main results that you can quote from that era. Okay? So what are we going to do in this work? In this talk. Essentially what we're going to do is to study a particular class of non-holomorphic observables in four-dimensional n equals 2 superconformal field theories. Okay. So what we're going to consider is an n-point function, n plus 1 point function, where you have an arbitrary string of chiral operators and one anti-chiral operator. So these correlation functions are in CFT correlators what MHV amplitudes are to scattering amplitudes. This is essentially the amplitude that has all chiral operators and one anti-chiral operator. There you have all helices of one type except one which has opposite type. Just to set up some notations, in these four-dimensional n equals 2 superconformal field theories, superconformal primaries are annihilated by half of the supercharges of negative chirality. Alpha and alpha dot are spinor indices of opposite chirality, and A is a doublet index of the SU2R symmetry that any n equals 2 superconformal field theory has. So this correlation function essentially does not preserve any of the Poincare supersymmetries of the theory because O's preserve one half and O bar preserves the other half. Okay? And what we want to do is to compute such non-holomorphic correlation functions as an exact function of the coupling constants of the theory, which throughout the whole talk we will denote by tau and tau bar, okay? Which are again coordinates in the space of couplings, the conformal manifold M. Okay? So there are a few simple things that you can say before you start here. Unitariety of the Hilbert space of the superconformal field theory tells you that the dimension of these operators is fixed in terms of the U1R charge that also exist in N equals 2 superconformal field theory. So there is some simple selection rule about the charges of the operators that will give you a non-vanishing correlation functions. Okay. Geometrically, the chiral primaries, which are operators that cannot disappear as you explore in the modular space, can be thought of as sections of a holomorphic vector bundle over the conformal manifold, the space of coupling constants. And the connection in this vector bundle tells you how these operators mix with operators of the same R charge. The basic object that we will be interested in is the chiral ring of such theories. So the chiral ring the chiral primary operators define a chiral ring. Essentially, the product of two chiral operators decomposes into a sum of other chiral operators. So this is a commutative ring that has a product structure which is induced from the OPE of the conformal field theory. Okay? It is believed that for this type of chiral ring, the one I defined, which is annihilated by Q bar, say, that the chiral ring is freely generated. Namely, any element of the ring can be written as a unique polynomial in terms of a basis of generators. Okay? And it's manifestly true in Lagrangian theories. So what we can do is we can always choose a basis in the chiral ring where the OPE, in some sense, where you diagonalize the structural constants. Okay? So you choose a nice basis where the structural constants are diagonalized, but then the chiral ring data is still non-trivial and is encoded in the two-point function of arbitrary two elements in the chiral ring, one chiral and one antichiral operator. And this defines a metric, Gij bar, which can be interpreted as a Hermitian metric on the chiral ring vector bundle over the conformal manifold that I described. It is a simple exercise that I will not describe to show that, in fact, this more general class of correlation functions can be, if you know this data, the chiral ring data, you essentially completely determine that a special class of correlators that are known as extremal correlators. So if we're able to compute this data, we have solved for the chiral ring and for all extremal correlators. So let me give you an example, which is well known, of a type of metric in this vector bundle. So if we focus on chiral operators that have a certain dimensions where the dimension is 2, the metric associated to the two-point functions of a chiral and antichiral operator of dimension 2 determines what is known as the Zamolodchikov metric of the superconformal field theory. Okay? This is a metric which plays a prominent role in many places, and physically what it does is measure the distance in the space of conformal field theories. It has several beautiful interpretations, both in string theory and in other contexts. Let me just mention briefly a couple. So in two-dimensional string theory, the space of conformal field theories corresponds to the space of classical ground states of string theory. More specifically, if we focus on 2,2 superconformal field theories that describe a Calabi-Yau target space, this metric defines the metric on a Calabi-Yau moduli space. In 4 dimensions, there is a similar elegant interpretation of the conformal manifold, the space of 4-dimensional superconformal field theories, or conformal field theories, as the space of vacua in ADS-5 quantum gravity through the ADS-CFT correspondence. And in relation to AGT, for n equals to superconformal field theories, this metric has some relation with quantization of Teichmuller space. Okay? So one feature that will play an important role in our discussion is the fact that if you have a conformal manifold, so namely exactly marginal operators, that this Zamolodchikov metric gives rise to new conformal anomalies in your superconformal field theory. Namely, if you promote the coupling constants, the moduli of the superconformal field theory to fields, to background fields, there are new cohomology classes that appear in the conformal anomaly, namely in the trace of the energy momentum tensor. So in 2 dimensions, you essentially get something that looks like a sigma model, and this Gij is exactly the Zamolodchikov metric of the 2-dimensional conformal field theory. And in 4 dimensions, you get something a bit more exotic. It's a bidimensional analysis. It has to be a dimension 4 operator on the right-hand side. And essentially is a generalization of the fourth order Panitch operator that's known in the literature. Okay? So this homologic of metric has an elegant geometric interpretation and plays an important role in the study of conformal anomalies. Okay. So as I said, the chiral ring data and the extremal correlators in this 4-dimensional n equals 2 superconformal field theories. By the way, many of what I said can also be said about 2-dimensional n equals 2, 2 superconformal field theories, but just for concreteness, we will focus on 4-dimensional n equals 2 theories. All the data is captured in the 2-point function of a chiral and anti-chiral operator. Okay? So now the question is, how are we going to compute this data? So the basic strategy that we're going to use is to first, since the theory is superconformal invariant, why not conformally map it to some nice manifold that you can hold in your hands? So we're going to conformally map it from R4 to S4. This has one obvious nice feature that obviously since you put it on a compact space, the observable is infrared finite. And after all, wouldn't it be true naively that since these OIs in particular are primary operators, namely these are operators that transform very nicely under conformal transformations, shouldn't the mapping from R4 to S4 just be trivial and there is no subtlety? Well, it turns out that there are quite a few subtleties in this statement, and I want to mention them because I think it's interesting by itself, irrespectively of these applications to supersymmetry. It turns out that mapping correlation functions from R4 to S4 is afflicted by two related phenomena. One is the existence of ambiguities and new types of anomalies that lead to irreducible operator mixing when you study a superconformal field theory in a curved space. So let me just briefly give you a sense of what I mean by these words. So let's start with the basic object in conformal field theory, which is the generating functional of local correlation functions when we study a conformal field theory in a manifold X. And we have promoted the coupling constants to background fields so that if we want to study local correlation functions, all that I have to do is differentiate this object with respect to taus. Okay? Something that's basic about quantum field theory is that ambiguities in your definition of the theory are captured by local functionals of the fields. Okay? So now let's look at a particular local function that will be relevant for us. And these local functions that we'll discuss happen when the operators have very special dimensions, what we call resonant dimensions, like integer dimensions, essentially, which is precisely when you can have conformal anomalies. So let's look at a particular local functional that I am allowed and you're allowed to add to your path integral or to your definition of the connected generator of correlation functions. So let's consider that we have your theory has an operator of dimension 2, which is the case in particular of a 4-dimensional n equals to superconformal field theory that has an exactly marginal operator. And let's call tau2 the source for that corresponding operator. So by dimensional analysis, tau2 has dimension 2. So I can write down this marginal local functional constructed out of the coupling to the dimension 2 operator, the Ricci scalar on that manifold that has dimension 2, and an arbitrary function of the moduli. So these are, remember that tau and tau bar I are the coupling constants that couple to the exactly marginal operator. So this is a perfectly good local counter term that I can add to my theory. And it's an ambiguity. Of course, in R4, these local terms do not lead to any separated point ambiguities. I mean, such local counter terms in R4, since at the end of the day, I'm putting the backgrounds to 0, all that it does is affect contact terms. It gives rise to contact terms, and in conformal field theory, we typically do not care about meaningless contact terms. But in curved space, these local terms lead to separated point non-ambiguity. I mean, lead to separated point ambiguities. Namely, if I want to compute the 1-point function, in particular, of this operator dimension 2, and I differentiate with respect to the source that couples to it, that's going to induce a non-trivial 1-point function from the counter term. Okay? This can be interpreted as mixing of the operator O of dimension 2 with the identity operator on the sphere, which is the case I'll be caring about. Okay? So the fact that you are on a curved space tells you that local counter terms can give rise to certain ambiguities at separated points, which in flat space would be just contact terms. Okay. Following this logic, this mixing between an operator can be generalized when the dimension of the operator is any integer, and then any given operator of integer dimension can mix through an identical mechanism with operators of lower dimension in jumps by 2. Essentially, you need jumps by 2 because you need to insert some kind of curvature of the background there. Okay. Now, in a generic conformal field theory, which I mean a conformal field theory that has no further symmetries than conformal symmetry, this ambiguity can be removed, this mixing can be removed by a choice of local counter term, and then it's unphysical. The question is, what happens in a supersymmetric theory? So in a supersymmetric theory, the local counter terms should be supersymmetric. In particular, they should be n equals 2 supersymmetric. Okay? And one thing that you can prove is that there are no n equals 2 supersymmetric counter terms that you can write down that could undo the mixing that we have just described. The only ambiguity that you can undo is an ambiguity in these mixing functions that appear here by holomorphic terms, sum of a holomorphic and anti-holomorphic term. Okay. More incisively, supersymmetry relates the mixing counter term, the supersymmetric, the counter term that we were describing in the bosonic theory, to a cohomologically non-trivial Weil anomaly. Okay. So since it's relating it to a non-trivial, cohomologically non-trivial Weil anomaly, it means that it cannot be undone essentially by definition. A non-trivial cohomological class cannot be undone by a local counter term. Okay? And let me just give you an example. So let's consider the mixing of exactly marginal operators with identity that is related by supersymmetry to the conformal anomaly that I wrote earlier before in 4 dimensions. So the supersymmetric anomaly takes this form. Okay? So it's some integral over the entire superspace of some scalar function of the exactly marginal couplings. And sigma is essentially a super Weil transformation. Okay? So when you expand this thing out, it will spit out the Panaitz-like anomaly that we had before. And these plus terms will be the super Weil variation of the local counter term, which I cannot remove because it's related by supersymmetry to this one. Okay? So the conclusion of this logic is that operator on S4 is physical in n equals 2 theories, unlike in bosonic theories. So let me give you a local summary of the discussion so far. So what we have found is that the sphere background induces non-trivial operator mixing in n equals 2 theories. And if you want to compute correlation functions in R4, we will need to disentangle operator mixing to compute R4 correlators. The goal of this talk is to compute observables in flat space, and we're just using the sphere as a trick to extract the answer. So that means that in particular, we will have to perform some Gram-Smith generalization of the correlation function on the sphere. Okay? And this can be done sequentially because operators of a given dimension can only mix with operator of lower dimension. So all that we have to do is sequentially diagonalize the matrix of 2-point functions on the sphere dimension by dimension. Okay? But this still gives you the problem that you have to learn how to compute the 2-point function on the sphere, where you insert one operator at the North Pole and antichiral operator at the South Pole, how to compute this in a 4-dimensional n equals 2 superconformal field theory. Okay, so let me tell you how you can do this. So the strategy will be to take your superconformal field theory and essentially deform it by an arbitrary operator in the chiral ring. Essentially, the way you do it is that to any chiral operator, you can associate an n equals 2 supersymmetric invariant that I write roughly like this. So to any chiral operator, there is some Lagrangian that you can associate, which is n equals 2 supersymmetric. Okay? Since we are deforming by an arbitrary element of the chiral ring, which most of them are, of course, irrelevant, this reservation preserves a massive n equals 2 subalgebra of the superconformal algebra on the sphere. So SU2,2/2 is broken to OSP24, which is the massive algebra of a generic massive theory on the 4th sphere. You will need to then explicitly compute what this deformation term associated to a given chiral operator is on the 4th sphere. And essentially, it looks like a covariantized answer you would get for flat space plus corrections up to order 1 over r squared, where r is the radius of the sphere. So then, now that we have learned how to deform the n equals 2 superconformal field theory by an arbitrary chiral operator, we want to consider the following partition function. We want to consider the partition function of the superconformal field theory, again, which has exactly marginal couplings tau I, and deform it by arbitrary chiral operators in the chiral ring with coupling constants tau A. Okay? We will get a ton of mileage from the following interesting curve space word identity. So let me just mention it because this plays a key role in getting to the answers. And so this word identity makes the following observation. It tells you that if you compute the correlation function of Lagrangian insertions associated to a chiral and anti-chiral operator, and you integrate the local Lagrangian over the sphere, so this is an integrated correlation function. This is, by a word identity, a subtle word identity, the same as computing the separated two-point function of the chiral operator itself, one evaluated at the North Pole and one evaluated at the South Pole. Okay? So it relates this integrated correlation function to a separated point correlation function of the chiral primaries, which is the object we were aiming to compute. So now I have related some, essentially by the usual relation between integrated correlation functions with derivatives with respect to couplings. I mean, this side is nothing but differentiating the partition function with respect to the couplings. That brings integrated Lagrangians. We have related derivatives of the partition function to chiral primary correlators. Okay? So if we now know how to compute the S4 partition function with arbitrary sources for chiral operators and do the diagonalization procedure, then we will have an answer for what the chiral ring and the extremal correlators are for the n equals 2 theories. So let me give you a little lemma that follows from the discussion we had so far. Consider now the chiral operators of dimension 2. I already said that dimension 2 chiral operators control what's the homological metric of the conformal field theory. So now we're studying the conformal field theory on S4. And on R4, we want to compute essentially the two-point function of dimension 2 chiral primary operators that defines the homological metric. We're going to get this from the sphere by diagonalizing, by undoing the mixing that the sphere produces for you. So essentially what I have to do is consider the metrics of two-point functions that explains the mixing between the dimension 2 chiral primaries with the identity operator. The dimension 2 operators can only mix with the identity operator and, of course, with other dimension 2 operators. So obviously, this is just the two-point function of the identity. This is the one-point function of O, the one-point function of O bar, and this is O bar evaluated on the sphere by the word identity I just described. And if you remember Gram-Smith, the norm of the orthogonal eigenvectors is the determinant of the matrix. So if you compute the determinant of this matrix and you do a simple arithmetic, you can write it as d tau bar of the logarithm or the S4 partition function. So you see that this logic of anomalies, mixing, and word identity gives you another proof of a relation that tells you, that gives a geometrical interpretation to the S4 partition function of an n equals 2 superconformal field theory. It tells you that the S4 partition function of a superconformal field theory measures the Keller potential, because the metric on the conformal manifold of this theory is a Keller metric, computes the Keller potential on the conformal manifold. This R is the radius of the sphere, and A is the usual Euler anomaly for dimensions. I already said this. So K is the Keller potential on the conformal manifold, and the virtue of this is that due to the work of Peston, notice that in here I did not need to know how to compute the ZS4. I'm just using word identities to find a relation between correlators in R4 to correlators on the sphere. But in this case, we can compute it exactly for these dimension 2 operators because Peston computed for us the S4 partition function. Okay. So this logic allows you to compute the metric on the conformal manifold in many theories, including incident corrections. So this story is a four-dimensional avatar of a two-dimensional older story that related the two-sphere partition function of 2,2 theories that you can define. There are two types, depending on what supersymmetry you put on the sphere. that compute, if the 2,2 theory is relevant, describes Calabi-Yau target spaces, that computes either the Keller potential on the Keller moduli space of the Calabi-Yau or the Keller potential on the complex structure moduli space. And in this case also, since we know how to compute exactly by supersymmetric localization both types of partition functions, this gives you a way of computing these metrics on Calabi-Yau moduli spaces. And an interesting application of all of this was a new way of computing old and new Gromov-Witten invariants for Calabi-Yau manifolds. Okay, so far what I've done is to show you that if we're able to compute the S4 partition function of the deformed n equals 2 superconformal field theory, we will be able to extract through some Gram-Schmidt procedure the chiral ring and the extremal correlators of n equals 2 theories. It turns out that this is not very hard, because the hard work was done by other people. It's not very hard to compute the S4 partition function of this deformed theory. Essentially, you can just generalize Peston's computation and get the answer. Okay? So the answer looks, again, as some kind of matrix integral over the partition function in the omega background, one residing at the North Pole and one residing at the South Pole. Just without getting into lots of details, this formula, the one loop part of the answer in this localization computation will be exactly the same as Peston, because I can use the same Q-exact deformation term that he used. And of course, the thing that will change will be the classical action, which now is deformed by the higher chiral operators. Sometimes these are known as higher Casimirs. And of course, this also changes quite dramatically, because I have to learn how to compute instant on partition functions in the presence of higher Casimirs. But this was done by Nekrasov with many collaborators, and some of them are here, Nakajima, and so on. So this gives you a way. Of course, there's a subtlety that these computations for Z instanton were performed for theories that have a UN gauge group. And of course, superconformal field theories, you cannot have a U1 factor. So there is a subtlety of how you remove the U1 factor when you have higher Casimirs. But modulo that subtlety, this gives you the answer for the partition function. So let me give you some examples of the kind of answers that you can get out of this. Okay? Let's consider n equals 2 superconformal field theories which have a one chiral ring generator that has dimension 2. So in a Lagrangian theory, it will be something like trace of phi squared, where phi is the complex scalar in the vector multiplet. Since there's a single dimension 2 operator, this theory has one exactly marginal coupling that is obtained by complexifying the theta angle with the Yang-Mills coupling constant. Okay? And this complex constant takes values in some upper half plane. Okay? The basic, I mean, the two examples that describe this situation is n equals 4 SU2 super Yang-Mills and n equals 2 SU2 super QCD, which is an n equals 2 vector multiplet coupled to 4 fundamental hypermultiplets. In this case, the chiral ring OP is extremely simple because at any given dimension, there is a single chiral operator. So the OP is extremely simple. You have the product of ON times OM defines the operator ON plus M. And our goal is to compute this matrix element, okay? Now, by virtue of the word identity that I described earlier, the 2-point function on the sphere is given by taking some tau and tau bar derivatives of the S4 partition function. Okay? And now, again, if you look at how Gram procedure works, you can always write the norm of the eigenvector of the orthogonal vector as the ratio of determinants of two different neighboring subblocks in the Gram-Schmidt decomposition. So that means that the metric on the chiral ring vector bundle can be written very nicely as a ratio of determinants of derivatives of the S4 partition function. And if you know something about integrability, which I don't know very much, but enough to realize that this leads to an interesting connection with integrability. This structure of writing answers in terms of ratios of determinants is kind of a hallmark of integrability. In fact, you can prove that the chiral ring data, namely this matrix G2N, are acted on by integrable differential operators. For this simplest case of one-dimensional conformal manifold, the differential operator you get is a Toda chain. Okay? So you can represent your chiral ring data in terms of particles that live on the line, and that interact with each other through this potential, okay? And these variables Qn can be written in terms of the metric in this particular way. So the chiral ring data for this theory is labeled by, is governed by a set of oscillators with a prescribed dependence on the leftmost oscillator, which is fixed by the S4 partition function. This derivation, this kind of differential equation was derived earlier by Baggio, Narcos, and Papadimas using a kind of a heavier machinery of 4-dimensional equals to TT star equations in the holomorphic gates. Of course, the TT star equations do not tell you what the answer to the problem is. You still have to find a solution, and the S4 partition function is giving you the right solution to the problem, okay? So this means that what I essentially have shown you is that for this particular example, if you know how to compute the S4 partition function, which we know, you have an exact solution for the chiral ring. The story of integrability, how much time do you have? 15? 20. Oh, 20, okay. So I can go more slowly, that's good. The thing that you can show is that the chiral ring data of any 4-dimensional equals to theory is acted on by an integrable system. Essentially, what you can show, but this is very easy, that the TT star equations of 4-dimensional two theories are essentially integrable. For n equals 4 super-Young mills, for any Gates group, not only SU2, what you get is a series of decoupled Toda chains. But for example, not for the simplest order theory you can think of, which would be n equals 2 SUN super QCD with 2n fundamental hypermultiplets. Okay. One thing that generalizes to any theory by virtue of that word identity is the fact that you can write down the chiral ring data of any n equals 2 theory as a ratio of determinants of the derivative of this deformed partition function. So this gives you a procedure, an algorithm to compute the extremal correlators in n equals 2 theories. So let's now look at some examples of how this works. Let's consider the simplest possible n equals 2 theory, which in fact has n equals 4 supersymmetry, which is n equals 4 super-Young mills with arbitrary Gates group G. In this case, the chiral ring is not that exciting because the chiral ring is 3-level exact. It means that it receives no perturbative or non-perturbative corrections, as was conjectured by these authors and proven by these other ones. But actually, this observation played a very important role in the early days of ADS-CFT because it allowed you to test ADS-CFT by comparing an answered weak coupling to an answered strong coupling. In this case, there's a homological metric. So again, this theory only has, if G is a semi-simple Lie group, it only has one coupling constant. The homological metric on the conformal manifold is just the Poincare metric on the upper half plane. And the curvature is determined by the central charge, the A or the C central charge of the n equals 4 theory. Now let's consider n equals 2 SU2 super QCD. So again, this we're computing by doing Gram-Schmidt on the sphere. In this case, the metric starts with the metric on the upper half plane, but in this case receives an infinite series of perturbative corrections that in particular, after you do all this diagonalization game, reproduces explicit Feynman diagram two-loop computations that were done before, and of course generalizes them to arbitrary order through this Gram-Schmidt procedure and the sphere partition function. You can also, given that we have the explicit formulas, you can also compute, if you like, instanton corrections to the homological metric for this theory. Another interesting example to keep in mind is the case of super QCD with Gates group SUN. So this theory is superconformal if the theory has 2n hypermultiplets in the fundamental representation. There are several important differences in this theory compared to the other ones. One of them is that, first of all, the chiral ring has now n-1 generators. Essentially, there is one generator for each Casimir of SUN, so trace phi square up to trace phi to the n. And therefore, any element in the chiral ring can be written in this way. So by an arbitrary polynomial of the generators in the chiral ring. So it's labeled by you can label every operator by a set of integers. One important difference also with the other case is that now you can have degeneracies in the spectrum. In the case of a single generator in the chiral ring, there was only one operator of a given dimension. Here, of course, you can have degeneracies because when you start multiplying different generators in the ring, you can get operators of the same dimension. So for example, in dimension 6, for SU3, you can get phi 2, 3 and phi 3, 2. So the trace phi squared to the cubed or trace phi cubed squared. Okay? So this is also something that you have to learn how to deal with on the sphere, which we know. Okay? And again, using the Gram-Schmidt procedure, you can compute the chiral ring of any of these guys to arbitrary order, and here I just write numbers to show you that can be done very explicitly. Okay? So now that you have an exact formula for correlation functions in four-dimensional quantum field theory, this is a good laboratory to test various ideas and conjectures in quantum field theory. So what you can do is explore the Borel summability of the perturbative expansion of these local correlation functions. Okay? So that's something that you can do very easily because you can numerically integrate that integral to very high precision and test, for example, show that in this case, the series is Borel summable. Another neat thing that we did, given that you have an exact result, is we analyzed the convergence of the Padé approximation to the perturbative series. So essentially, there was an old conjecture made in QCD perturbation theory in which getting from loop n to loop n plus 1 is exponentially hard. So at some point, they came up with some conjectures of how could they guess the nth plus 1 order given the nth order. So they made some conjecture about how the extrapolated Padé answer at n plus 1 order differs from the exact answer. And the conjecture was that it's exponentially close, and indeed, that's what we tested in this example. We see that the convergence of the Padé approximation is exponentially close to the true answer. Very good. So now we get to some conclusions on open problems. So more or less, the problem of determining the chiral ring data is essentially solved through this deformed partition function on the fourth sphere. Okay? One of the key ingredients in understanding how to relate the chiral ring, which is an observable of the flat space theory, to the short partition function, was to understand the role of mixing and anomalies once you put the superconformal field theory on the sphere. Okay. One of the applications of this work is that it gives geometrical properties of the conformal manifold. Very concretely, it allows you to compute the metric on the conformal manifold, which is something that, well, in some sense, is a generalization to, you can think of the metric of the conformal manifold as a generalization of the A and C anomalies of four-dimensional quantum field theories, with the important difference that the A and C anomalies are constants on the conformal manifold, while the metric depends, of course, non-trivially on when you are in the conformal manifold. So not only can you use these kind of arguments to extract geometrical information about the metric, geometrical information about the conformal manifold, you can use physical consistency conditions to make educated guesses about what is the topological properties of the conformal manifold. And essentially, consistency of the anomaly implies that the Kähler class on the conformal manifold should be trivial. So that's also something that just follows from demanding that the anomalies that you defined somewhere in the conformal manifold are consistent and do not lead to physical pathologies. Okay. The other thing that we saw is that chiral rings in n equals to superconformal field theories come equipped with an integrable system that can be derived from the TT star equations. Okay. In the simplest cases, you get semi-infinite Toda chains, but in general, you get a more complicated systems, integrable systems of Hitchin type. Okay. The fact that you have explicit answers allows you to test and maybe even make new conjectures about the behavior of quantum field theory, both at high orders in perturbation theory, but also at finite coupling. Even though technically, of course, computing these integrals at finite coupling becomes technically challenging. Okay? Many of these ideas that I described can be extended to the chiral ring of 2,2 theories. There, new elements appear. There are many elements that are different, but one main qualitative difference that appears there is that we know that the chiral ring we believe that the chiral ring of 4-dimensional n equals 2 theories is freely generated, but we know that the chiral ring of 2-dimensional n equals 2,2 superconformal field theories has relations. And there's some interesting story of how this Gram-Schmidt procedure is able to fish out those relations by extending this logic. Okay? Another interesting connection that so now you can make connections to all kinds of things. I'll just mention a few. Since we're computing the S4 partition function, the scalar potential through the AGT correspondence is related to in some sense, a quantization of Tagmurer space. So the scalar potential would be like a quantization of the usual Weil-Peterson metric on the modular space of Riemann surfaces. So there is some relation there that I think could be made more precise. Another interesting connection that you can make using this work is with the conformal bootstrap program. So this is a non-perturbative approach that only has an input conformal symmetry that in principle determines correlation functions in conformal field theory. And essentially, one possible application of our result is that it gives input, like initial data, to use in that conformal bootstrap program. Okay? So, but of course, there are still many open problems that remain. One of I'll just mention a few. So one important problem is that how to really compute instantons in the omega background for SUN theories when you have higher Casimirs. Another thing that I didn't explain in a lot of detail is that I mentioned that we're able to understand how anomalies work when we have these dimension 2 chiral primaries. But there is an open problem to write the non-trivial cohomology classes associated to the conformal anomalies of higher chiral primary operators that would be interesting to write down. So essentially, what is the generalization of this formula for higher dimensional chiral primaries? So that's something interesting to work out, both in 2 dimensions and in 4 dimensions. Another possibility is to, since we have explicit formulas, you can try to study the large n limit of these formulas. Notice that this was all finite n, including SU2, but one interesting application of taking the large n limit is that you can make connections with ADS-CFT. You can try to relate our correlation functions to correlation functions that you can compute in ADS-CFT. And finally, these chiral primary operators should have nice transformation properties under S-dualities of the n equals 2 theories. And this implies interesting modular properties of these correlation functions that we computed, which would be interesting to explore. So with that, I'll conclude. Thank you.
Thank you very much. Are there questions?
About the conformal bootstrap, so I'm not sure how you want to get exact correlation functions. Usually, crossing symmetry imposes inequalities, and yes. I understand that your theories are well within that interior region of those inequalities, so probably they're not on the boundary.
No.
But my real question is actually about resurgence. So you get this beautiful expansion, say, for SU2 super QCD, and you can basically take the perturbative answer, feed it in the resurgence program, and first question is it Borel summable?
Yes.
If yes, what are the poles? Do you see renormalons? Do you see just instanton effects?
You get poles in the negative real axis. Poles in the negative real axis, not renormalons.
Quick question on your final comment. So if you're computing the chiral ring of a conformal field theory that has dualities, I would have expected the chiral ring to be invariant, but are you suggesting there's some modular?
Well, what I'm suggesting is that the first question you have to understand is how does S-duality act on a chiral operator? And what we believe we know, at least in examples like n equals for superior mills, is that a chiral primary operator transformed under S-duality as a singlet under S-duality, but it transforms as a modular form with a weight, which is determined by the dimension of the operator. So I'm just saying that this should something that this modularity property is something that could, in principle, explore more explicitly.
Actually, my question was closely related. So could you go back to the metric that you, the Zamolodchikov metric you had for
which one do you like
SU2?
Better?
Yeah, good.
This one?
So when you say, this is superconformal, right?
Yes.
So isn't that metric supposed to be giving us, isn't the metric supposed to be invariant under some S-duality action?
Well, this is not unrelated to the question, is the partition function S-duality invariant, or it transforms as a modular form? As you know, the partition function of S-duality, the theories that have S-duality, have certain subtleties, whether they are invariant or they are modular forms. Like, for example, in the work of Witten of abelian gauge theories. So that's the subtlety I'm describing.
Well,
yeah, in the most naive form, it should be the partition function should be invariant.
No, but we understand that subtlety. I mean, you know,
yes?
we understand what the modular weights are in terms of the Euler character and the signature.
Yeah, so it has to do with.
But I mean, this. If I look at this metric on the tau plane, how in the world is that going to be modular? That's perturbative plus instant. Ah, yes, thank you. Thank you. So you're saying the whole sum.
Of course.
Yeah, good. So still, so the G. Okay, so you haven't. Wait, I thought you said you'd worked out the chiral, the G2 metric exactly. So I mean,
no, exactly.
I thought this was just
so
you were just showing us some pieces that you were extracting from the exact answer.
Yeah. So this is the expansion of G2.
Yeah.
Around the infinite weak coupling cusp.
Okay, but you know the full series,
what you know is an integral. You have an exact formula for an integral that you could numerically integrate if you wanted to compute the metric anywhere. Like, what is it?
Well, I think I completely missed the whole point of the talk. I thought you got Z of S4,
yes,
and then from Z of S4, you actually knew the exact formula for the Zamolodchikov metric.
But the exact formula means that I know
modular,
Z4 right? Exactly, but now you have to evaluate this integral, right? And if you want to compute at some random point in the upper half plane, you need to have to express Z instanton near that point, right? So Z instanton is usually presented to you as an expansion around weak coupling. That's what instantons are, expansion around weak coupling.
Okay, but you can still look at the expansion around weak coupling and ask if this thing could be modular.
Yes, yes. So that's why I leave it as a yes. That's what I'm saying, essentially.
Are there more questions?
I just wanted to ask how reliable is the claim that the Keller form is exact?
It's a physical argument. We don't have a. I mean, I don't think there is a mathematical proof of this one way or the other. It's an argument that follows from demanding that the anomaly. And essentially, yeah, so that the anomaly is invariant under Keller transformations. If the anomaly were not invariant under Keller transformations, it leads to some paradoxes that leads us to suggest that this. Well, okay, maybe we should discuss it in privately in the details. Yeah.
Are there further questions? If not, let's thank Jaume again.